question you might have had is like, why in redox reactions do metals lose electrons? Also, like, why does magnesium form magnesium 2 plus and not magnesium 3 plus or magnesium plus 1? Why do nonmetals take on electrons? And these are all really good questions. And here at the end of Chem 221, I'm going to try to answer these two questions using what's called ionization energy and electron affinity. And we're going to do a better job in future lectures in Chem 222 and Chem 223 to answer these. But for right now, the last two periodic trends, ionization energy and electron affinity, we can actually help answer these questions. Ionization energy is the energy required to remove an electron from an atom in the gas phase. And this is kind of a way that chemists use to talk about differences between removing energies. Now, if you have an atom in a solid phase, it's going to be a slightly different energy. But gas phases are generally easier to get these kind of data from, so that's why it's used. But do realize it's not always perfect. Ionization energies are always positive numbers. Removing electrons is an endothermic process, so keep that in the back of your mind.
To remove the outermost electron from a magnesium atom requires 738 kilojoules of energy per mole.
To remove the first electron from magnesium, it takes 738 kilojoules. Remember, an endothermic reaction, you can write the energy as a reactant necessary. Notice that magnesium plus was a little bit smaller than magnesium metal because you have one less electron. Those parent protons are holding on a little closer. 738 kilojoules, which is 738 kilojoules per mole, by the way, is a value that's not hard to get in a chemical reaction. Magnesium 2 plus, all right, is going to have 12 protons and 11 electrons. And we're going to see here in a little bit then that making magnesium 2 plus 1451 kilojoules, the energy required to remove that second electron higher than the energy for the first one. We would say that the ionization energy for magnesium plus is greater than the ionization energy for magnesium. The more protons you have, the higher they hold on to things. So removing electron from magnesium plus does take more energy than the energy to remove an electron from neutral magnesium.
Removing the second electron requires more energy, 1,451 kilojoules per mole.
When you get to magnesium 2 plus, you have a neon core, which is really good. And you can see that the sum of those two values is 2,100 kilojoules, something like that and stuff. To remove the third electron, making magnesium 2 plus magnesium 3 plus, look at the energy cost, 7,733 kilojoules. To remove the first two electrons, it was 2,100-ish kilojoules, and now it's 7,700 kilojoules. The energy gap going from magnesium 2 plus to magnesium 3 plus is quite large.
To remove a third electron from magnesium requires much more energy, 7,733 kilojoules per mole.
In chemistry, it's all about the energy. Having magnesium go to magnesium 2 plus is absolutely doable, 2,200, whatever, kilojoules. But to go from magnesium 2 plus to magnesium 3 plus, it's roughly 4 times as great, the energy. And that's something that just doesn't happen. So in chemistry, the oxidation number, the charge on the most accepted form of the ion, i.e. magnesium 2 plus for magnesium, is equal to the group number. All right, going to magnesium 3 plus is just crazy. On the other hand, having magnesium stop at magnesium plus 1 also doesn't happen that often. It's relatively easy to get 2,100-ish kilojoules of energy, so it's easy to pop that second one off, but it's very, very difficult to get the third one off. So scientists use ionization energy to tell which of the ion charges are most likely. This graph here shows trends in the ionization energy, and technically it's the first ionization energy, i.e. how much energy it takes to remove one electron. And so hydrogen, you can see, is the purple box right there, and it's pretty good. Lithium is a lot easier to remove an electron, and sodium is easier yet, and potassium is easier even on top of that. And if you look at this thing long enough, and this is an ugly graph, we end up seeing kind of two things. I mean, generally speaking, these ionization energies are going down as you go left on the periodic table, and generally they're going down as you go down the periodic table. So when it comes to ionization energy, we say that ionization energy gets smaller as you get left and down, or it gets larger as you go up and to the right. And you can think about it either way. Now, these are all first ionization energy, which means one electron removed. And in theory, we could do the same thing with second ionization energy and see something kind of like this. So ionization energy increases as you go right to left. So ionization energy increases as you go right across the periodic table. Z star is something called the effective nuclear charge. It is also increasing. Don't worry about that too much, but it's another factor that makes ionization bigger. So metals generally just lose electrons. They lose them more easily than the nonmetals, because the nonmetals on the upper right side are harder to have them remove electrons. So metals lose electrons because their ionization energies are lower. Metals are good reducing agents, i.e. they like to be oxidized, i.e. they like to lose electrons. Metals are also good at allowing other things to be reduced. That's why they're called reducing agents. I hate that, but that's okay. They allow other things to be reduced because their electrons are somewhat easy to remove. Nonmetals can lose electrons, but it's more difficult. Usually it takes higher energy. Ionization energies increase up a group. All right, so again, up and to the right is how we're going to do it. And so it gets generally harder because electrons get a little closer basically to the protons. That's what this particular thing is saying. Again, the idea is up and to the right. That's the trend in ionization energy. Here's another problem. Comparing these elements, which one has the largest first ionization energy? So we're comparing the energies to remove the first electron. And the punchline here is that you want the element on the periodic table which is most up and to the right. So literally look on your periodic table. Sodium, as we saw earlier, is most left and down. Then aluminum, then boron, and carbon is the most up and to the right element in that list. So we would say that carbon has the highest first ionization energy. And again, there might be individual trends which would break that, but overall this is a pretty good pattern to follow. Alkali metals react readily with water, and because of the lower ionization energy, potassium reacts a lot quicker with water than lithium does. And this is just a fun set of videos that shows the difference between lithium, sodium, and potassium. Lithium has the highest ionization energy cost, so it's the hardest to remove the electron. On the other hand, potassium is pretty easy to remove the electron. It's a lot more exciting.
Lithium is the first of the Group 1A metals. It reacts with water to form lithium plus 1 ions, losing an electron from a 2s orbital. Compared with sodium and potassium, lithium reacts rather slowly. Sodium is the second of the Group 1A metals, occupying a position just below lithium on the periodic table. When it reacts with water, it loses an electron from its 3s orbital. The reaction of sodium with water is more vigorous than that of lithium. Potassium is the third metal in Group 1A. Lower than both sodium and lithium on the periodic table, it is even more reactive with water. The valence electron lost by potassium upon reaction with water comes from a 4s orbital.
Couple of things about these videos. First of all, you could totally see that lithium was not as exciting, if you will, as potassium. All right, potassium reacted a lot quicker, sodium in the middle, lithium not as much. The metals were being stored in a liquid, and that liquid was obviously not water. I want to make sure that's clear. That was a type of a mineral oil, something that doesn't react with the metal. So yeah, they certainly were not storing them in water. And then, yeah, you could tell that potassium had a little bit of a red flame to it. The red flame is due to the sharp line spectra for potassium. When you take the different colors from potassium, put them together, it's kind of a red color. Sodium is kind of a yellow color, and I think lithium is kind of a red, but I didn't see too much of it. Finally, all of these metals are actually less dense than water. So they all like float on top of water, which is very cool and very unusual. Honestly, most metals sink to the bottom. They're more dense than water, but these are actually examples of that. So again, because the ionization energy for potassium, the first ionization energy of potassium, a lot less than sodium and definitely less than lithium, that's why potassium was more reactive. It was ready to rock and roll, and lithium took a little bit longer to kind of get in gear. The last periodic trend we're going to look at is called electron affinity, and some types of elements actually give off energy when they gain an electron. And I like to think about this as the cool kids on the back of the bus. Some of the atoms really want to be like the noble gases, and they're so excited they give off energy. I don't know if that works for you or not. But anyway, a few elements will actually gain electrons to form atoms. So for example, these aren't going to be metals. Metals form cations. But the nonmetals will gain electrons to form anions, and they'll actually give off some energy when this happens.
When a gaseous atom accepts an electron to become an anion, the energy it releases is a measure of its electron affinity. For chlorine, this is minus 349.0 kilojoules per mole.
So in this example, the gaseous A, what G means gas, would be chlorine. It gained an electron to become chloride, and energy was released in this system. It's actually usually exothermic. The energy, electron affinity here, the E sub A, is equal to just a change in energy. It's often exothermic, at least when it's interesting, but it can be endothermic as well. Electron affinity, I honestly believe, is the weakest of the four periodic trends, but it can be useful to explain why nonmetals like to gain electrons. Here's an example of oxygen becoming the oxygen -1 ion. So this isn't a true oxide at -2, it's just O -1. But it is exothermic. You end up giving off -141 kilojoules per mole, which is very exothermic. And this is really the case for a lot of the nonmetals. However, this trend is really strange. If you go from nitrogen to nitrogen -1, you actually don't have a gain or loss of energy. It's almost like that extra electron just fits in and everybody's like, yeah, whatever. This is an unknown mechanism, and that's why electron affinity is a little bit strange sometimes to talk about. Here are values for electron affinity and stuff like that. Some of these numbers have been calculated and some of them are actual. Again, these numbers are kind of embarrassing here, but generally speaking, electron affinity increases as you go up and to the right. And again, there's so many exceptions to what I just said, it's embarrassing, but kind of go with the flow. The noble gases here don't count at all in this category because noble gases don't gain or lose electrons by default. They're stable, all right? But if you look at everything but the noble gases, then kind of going up and to the right is kind of right. But again, like I'm kind of embarrassed even to show this slide. However, electron affinity can be used to see why nonmetals like to gain electrons, all right? So you can see over there on the right, like fluoride, chloride, bromide, they have very negative numbers. They like gaining electrons. They're really happy. They want to give them off and stuff. So again, this is kind of embarrassing to talk about as an instructor, but the idea is for electron affinity up and to the right. Okay, let's repeat after me. Trends in electron affinity, it gets bigger up and to the right on the periodic table. Here's another embarrassing graph. Sorry, I'm being really cynical. This is bad. Again, like I said, generally things are getting bigger as you go up and to the right. and that kind of works, but obviously it's not perfect. Oh, brother. Oxygen is lower than sulfur. Carbon's lower than silicon. Anyway, obviously I hate this electron affinity talking about it as instructor, but again, this is the official dogma. Chlorine is actually the highest electron affinity. It's higher than fluorine, which also doesn't make any sense to me, arguably. But anyway, just realize that it is one way that can be used to justify why nonmetals like gaining electrons, but obviously it's not perfect.
The reaction of sodium and chlorine is governed by the arrangement of the electrons of each species about its nucleus. Chlorine is an oxidizing agent because it has a high electron affinity. Sodium is a reducing agent because it has a low ionization energy. The redox reaction produces the ionic compound sodium chloride, which contains one sodium ion and one chloride ion.
Despite all my earlier cynicism, we can explain then why sodium and chlorine make sodium chloride. All right. Chlorine likes to become chloride. It has a very exothermic electron affinity. It likes gaining an electron to become Cl-. And it releases so much energy that then it's easy for sodium to give up its electron, making sodium ion, because it has a relatively low ionization energy. So when you have the perfect combination of ionization energy and electron affinity, you can then make these kind of reactions happen, and they can be used to predict formulas. So it is a tool that's being used. Obviously, it's not perfect. We should look at the actual lab results probably more than anything. Anyway, cool.